Okay, so let's get going then. So welcome everyone. So today we'll have Jeff Hicks from the University of Edinburgh, and he will talk us about either superabundance or non-superabundance and unobstructedness. Okay,
Great.
please.
Great. Well, thank you very much for the invitation. It's a delight to be visiting Kansas virtually. If you have any questions at any point of the talk, please don't hesitate to stop me. I've been informed that there is a soft deadline of an hour, so we should have a little bit of time in the middle of flight to make some course corrections if we need to. Today I'll be talking about non-superabundance and unobstructedness. The talk is going to have 4 parts. The first part, I'm going to talk about A and B realizability. And the second part, I'm going to talk about an unobstructedness condition. Where I will define what unobstructedness is. In part 3, I'll talk about disks with tropical Lagrangian boundary. And in the last part, I will talk about the title of this talk. Okay. So, and also, if you can't see the boards or anything, let me know, and I can write a little bit larger and see if that will work. Okay, so the setting for today is I'm going to be working with Q. This is going to be an integral affine manifold. And by that, I mean that there's going to be a lattice inside of the tangent bundle of Q, which is full rank and integrable. So from this data, I can cook up a pair of spaces. The first space is XA, which is defined to be equal to the cotangent bundle of Q mod the dual lattice. So this is naturally a Lagrangian torus fibration, right? The cotangent bundle is a symplectic manifold. The fibers, the cotangent fibers are Lagrangians. I take the cotangent fiber and I'm going to mod out each one by the action of a lattice. So that's going to give me a torus. So this is a space fibered by Lagrangian tori with base Q. The second space that I'll be considering is XB. So this is TQ mod N. This is naturally a holomorphic manifold. And the reason that I could put that condition of holomorphic was that I said that this lattice over here was integrable. So let me write. This is symplectic. This is complex. And the last thing that I'll be doing in this talk is I'll be talking about subvarieties of Q. These are going to be some tropical subvarieties. The statements in this talk will be true for various different conditions that you put on this tropical subvariety. Maybe that you require them to be dimension 1. Maybe you require them to have a pair of Pants decomposition. Maybe you require them to be trivalent. So for this talk, I will always just consider this to be a trivalent smooth curve. So a curve that has a pair of Pants decomposition, kind of the nicest setting that you could look at. But a lot of the statements can be generalized to weakening those conditions. Okay, so with that set up, I can start to describe what the A realizability and the B realizability problem are. So the more familiar one is B realizability. which asks the following question. So, given V inside of Q, does there exist YV inside of XB, which tropicalizes to V? And I'm going to be a little bit vague about what tropicalization means here, but maybe the intuition that you have is that in some sense, if I take the projection from XB to Q, and I apply it to the set YV, that this is kind of approximately V in some sense. So the image approximates V.
Can you, Jeff?
Yes.
Can you be less vague about what you mean by tropicalization? Tropicalizing.
Sure. I am not going to talk about B realizability outside of this one slide. But if you want, what I would really like, I would take XB to be some kind of rigid analytic space, which has a local, like an aphanoid, which has local aphanoid charts, which glue together to give me Q. And then this tropicalization would be the valuation. And then I would replace this with an equality. And then YV would be some kind of analytic subvariety.
Because I'm assuming you're going to talk more about the A side, right? So
Yes.
then you also want to some sort of limit. Would you be less vague at that then?
Yes, on the A side, I'll be completely rigorous. Yeah.
Thank you.
Yeah, great. So, right. And maybe actually one of the reasons I have to be a little bit vague here is that there are a lot of results about when you can realize something, but usually they're written for maybe different versions of what the word tropicalized meant, depending on what was around in the literature at the time that the result was written. Now, the question has a short answer. Can you always do this? And the answer is not always. So, Halkin in some of his early work gave an example of this. So there's an example of a so-called superabundant tropical elliptic that is non-realizable. Asking under what conditions you can take one of these V's and realize them is an interesting problem. For instance, if the dimension of Q is 2, then the answer is always. If the genus of V is 0, the answer is always. And the other condition is if V is non-superabundant and trivalent, then you can lift it. So this is just providing some context for what happens on the B side. Now let me give a definition of what happens on the A side. So you could similarly ask if you could do this problem in geometry, where it becomes the following. So for A realizability, the question is, same starting point, given V subset Q, can you find, and now instead of looking for some complex subvariety, I'm going to instead look for a Lagrangian submanifold. Can you find a Lagrangian submanifold LV inside of XA that it tropicalizes V. Okay, great. And now the point that is that I am now hiding a lot in this word tropicalize over here, so maybe I should say what this means. Okay, so the first approximation that you could take is that maybe you just ask that, if I take the projection pi a from xa to q, and I apply it to LV, I get something which looks approximately like V. The problem with this is that if I mean by approximately, I mean like maybe like lives within a small neighborhood of V, then actually for any subset V inside of Q, I can find a Lagrangian that does this. So it's not a very good definition. The next better definition that one could come up with is the following, which is let V1 be the top dimensional strata of V, then define LV1 to be equal to something like the conormal bundle to V1 mod the conormal lattice perpendicular to V1. That lives inside of XA. And then you could ask, does LV equal LV1 outside a small neighborhood? Okay, so this is a much more precise definition of what it means to have a Lagrangian lift of some tropical subvariety. Namely, for affine spaces, we know how to produce. For affine subspaces, we know how to produce Lagrangian lifts, and so to be a Lagrangian lift on a tropical thing means that at least over every affine subspace, you must agree with the lift that I know how to produce. Is that a satisfactory definition for what a realizability might be? I mean, it's still not completely precise. I can really spell this out in more detail if you would like, but does this have a kind of enough shape to go forward?
It's a good definition, but I'm worried that if it's ever possible.
Yeah, right. So this outside of a small neighborhood, maybe I should put some more words down. Okay. So outside of a small neighborhood. So outside of a small neighborhood of pi, so outside of pi a inverse of a small ball of V minus V1. Okay, so the kind of the picture that I have is here's my tropical subvariety V, and then when I want to build the Lagrangian lift of it, I say, well, I can take out some small ball over here, and then I ask, over these three edges, that my Lagrangian look like kind of the standard lift. And then I say, and then I actually don't care what you do at all in the middle. Do whatever you can in the middle to fill that by a smooth Lagrangian, and that's the Lagrangian lift. And if you can do it in a way that I can choose this ball to be arbitrarily small, then we'll say that you've produced the Lagrangian realization.
Okay, so
Right.
so I give you any epsilon, and then for any epsilon you would be able to that's the question you're asking. I give you epsilon, and then you're answering that for
Yeah.
whatever I give you, you are able to do that.
Yeah, and in fact, for any choice of epsilon that you give me, if I want to be very precise, for any choice of epsilon that you give me, any construction that I should give you a family of things which are Hamiltonian isotopic and would be satisfied for any epsilon. So by applying a Hamiltonian isotopy to this LV, I can make that ball smaller and smaller. So it's really a family of Lagrangians which kind of approach this in some limit.
Good, thanks.
Great. So it seems like kind of off the bat that this is a tricky thing to do. But as I've written the definition over here, the answer, again, initially due to Grisha, and then in some more generality for other types of tropical varieties, I work from Matesian out of my thesis, says essentially always possible. So unlike in this case over here, where I'm not always able to lift some tropical subvariety to an algebraic subvariety or an analytic subvariety, over here, no matter what tropical curve you give me, if it's three-valent and smooth, I can always build the lift of it. And this is a little bit disconcerting if you're really invested in mirror symmetry, because you would expect that these objects are going to be mirrored to something over there. Okay. So something must be going wrong. And the problem is that the Lagrangian submanifolds that you build, they kind of look very nice from a differential geometric point of view. They're smooth, embedded Lagrangians. But from a symplectic geometric point of view, they're quite bad. All of these Lagrangians bound holomorphic disks, which are kind of the bane of symplectic geometers. So if you add an additional condition on this, so instead of saying a Lagrangian submanifold, I say unobstructed Lagrangian submanifold. That's a symplectic geometric condition that I'm going to outline in a moment. Then it is not always possible. And in fact, if V has an unobstructed A realization, it implies that it's B realizable. So you can kind of easily produce Lagrangian submanifolds which lift V, but producing Lagrangian submanifolds which satisfy this further unobstructedness condition is tricky. And how tricky is it? Well, every time you do one, you're able to solve a realizability problem on the mirror side. Right. So today what we'll be talking about is this unobstructedness condition and how it relates to superabundance, which is this condition over here. Conjecturally, you would think that the conjecture that you would make, which I'm working on, is that B realizability occurs if and only if A realizability happens. So now I'm going to have to get to probably the most technical section of the talk. And I apologize in advance that I won't be able to spell out anywhere close to the right amount of details in this section. So, and this is to describe what is unobstructedness. What is this condition? So this is going to be some kind of purely symplectic geometric portion of the talk. Okay. So let L inside of X be a graded spin Lagrangian submanifold. So in the setting where you have a graded spin Lagrangian submanifold, then there's an invariant associated to it in symplectic geometry called the Fukaya A infinity algebra. The Fukaya algebra is triple CFL and K and a pairing where CFL is as a vector space, it's the ROM chains with Novikov values. These MKs are product operations on chains. So they're k-fold products from CFL, tensor itself k times to CFL in degree 2 minus k for all k greater than or equal to 0. And this is non-degenerate. Oh, this is the inner product. Okay, so that's the structure of the data. And now I have to tell you kind of what properties these data satisfy and how you build it. This algebraic structure over here is going to be a deformation of the de Rham cohomology of L. So you can see that the underlying chains are the same as the de Rham cohomology of L. But I'm going to take the regular exterior derivative on de Rham chains and wedge product on de Rham chains, and I'm going to deform them. And the way that I'm going to deform them is that I'm going to count holomorphic disks with boundary on L and use that to contribute to the algebraic structure. All right, so to define MK, do the following. For every class beta in H2 XL, you define NK greater than or equal to 0. Define a moduli space. I need a little bit more data, sorry. J, a choice of compatible almost complex structure. I consider the moduli space of maps from a disk with k+1 marked points to X, such that the boundary of the map is a subset of L, and the homology class of the map is beta, and that U is a J holomorphic map. So these moduli spaces naturally come with evaluation maps. The L, by evaluating at the output of the ith marked point. And then I need to use these evaluation maps and get some kind of operation on de Rham chains. So you define mk beta on chains x1 through xk to be equal to first I pull back differential forms xi to my moduli space along the marked points, and then I push forward that differential form along the 0th marked point. Then mk is defined to be equal to this the sum over all homology classes of mk beta weighted by the area of the class beta plus d if k is equal to 1, and plus the wedge product if k is equal to 2. Okay. Right, all right. Unfortunately, I have to put this definition up on the board. I mean, so if you're from the symplectic geometry crowd, then this is a tool that you've seen before. And for those of you who are not in the symplectic geometry crowd, this is a way that we in symplectic geometry take the de Rham cohomology of a Lagrangian and deform it in such a way that it remembers a little bit about the symplectic manifold. So you can think that you're using the de Rham cohomology of the Lagrangian to encode what kind of holomorphic disks can leave the Lagrangian and enter your symplectic manifold in different ways. Okay, so I've been saying that these are like Floer cochains, and I've said that this is some kind of algebra. The MKs satisfy a bunch of relations. The first relation that they satisfy is that if you look at the 0th term and you apply the first operation to it, this is 0. And the second operation that they satisfy is that if you look at the M1 term and you apply it to itself, you get the product of the M0 term with whatever you applied it to. So in a chain complex, you would have something like this M1 operation squaring to 0. And here you instead have that if you apply M1 twice to something, you get this expression, which is not quite squaring to 0. There's an error, which is that you have to multiply by m0. But the error is not so bad. The error itself is closed under the m1 operation. So this is kind of an analog to looking at, instead of like a bundle with a flat connection, looking at something like a bundle that has a curved connection on it. This over here looks something like the Bianchi identity. And this over here looks like the definition of the curvature tensor. All right, so let me get to what this unobstructedness is. In order for us to apply mirror symmetry to a Lagrangian submanifold, one of the conditions which is normally required is that we don't have a curvature term. So these Lagrangians are supposed to be mirrored to complexes of sheaves. And this condition over here says that if I give you a Lagrangian submanifold, I can pull an invariant out of it, but it doesn't look like a complex. It looks like this kind of curved thing instead. So we say that L is tautologically unobstructed if m0 is equal to 0. And we say that L is unobstructed by some element B in CF1 if B satisfies the relation m0 plus m1b plus m2bb plus m3bbb plus ... is equal to 0. And the reason that this unobstructed condition by B is useful is that we can associate the pair LB a new uncurved A infinity algebra. So maybe one way to parse this is that it could be that you have some kind of curvature term showing up, but maybe this curvature term looks like it's exact. And then you want to say that, well, while your Lagrangian is not tautologically obstructed, maybe it bounds some holomorphic disks. You could just imagine that maybe all those disks show up in pairs which cancel out to 0 in homology or something. And then you need another piece of data, B, that tells you how to cancel out those disk counts in pairs. And if you keep track of that all the way around, then you get some Lagrangian equipped with some data, which you can throw into the mirror symmetry machinery and start getting results with. So from all of this, I'm going to produce the following lemma. Whose proof is essentially in Fukai Otohona O. This is a variation of some ideas that they came up with, which is that suppose that the dimension of L is equal to 3, and that whenever boundary class of beta is not equal to 0, the moduli space is empty. Then there exists B making L unobstructed. Okay, so kind of the picture that I have in mind is that I said that this condition was something like the counts of holomorphic disks with boundary on your Lagrangian was null homologous. And the picture that you should have over here is that if this is your Lagrangian submanifold, the condition that I've said is that the only kinds of disks that we're going to allow on our Lagrangian submanifold so here's the disk up here. Are those which bound a closed cycle on the Lagrangian. So when you try counting them using something like cohomology, you end up having that count disappear. I'm happy to go through the proof of this if people would like, but I have a feeling that I should probably just take this piece of data as a black box and move back to something a little more concrete and geometric instead of kind of fluor theoretic.
What if dimension is not 3? Can you do something like that?
Yeah, so when the dimension is equal to 3, under the conditions I put for my Lagrangian, that it's graded in spin, then the moduli spaces of disks with one mark point as an output is 0-dimensional. Is 1-dimensional. And so knowing that the boundary of a disk contracts actually tells you that the evaluation map from the moduli space contracts. In higher dimension, then your moduli space will be like an S1 bundle over something kind of more sophisticated. And knowing that just like the boundary of a single disk and the moduli space contracts doesn't tell you actually that the evaluation map from the moduli space is null homotopic. There's something very nice that happens in dimension 3 that makes this work.
Okay, thank you.
Yeah. Okay, so let's go back to doing some kind of well, I'm going to leave that up on the board, but then I'm going to erase all of this kind of terrible fluor theory definition. Okay. So what we want is to kind of understand what kind of holomorphic disks can exist on the boundary of a tropical Lagrangian. All right, so remember before we have V inside of Q, some kind of tropical subvariety, LV inside of XA, a Lagrangian lift. Now, recall that I said that LV had to have projection. This is a projection pi A from XA to Q, which sends LV to a very small neighborhood of V. But a very small neighborhood of V is homotopic to V. And so I get an induced map from this. Something which I'm going to just abuse notation. I'll call pi A star from the homology of LV to V. sorry, homology of LV to the homology of V. Okay. And now what we can do is we can look at let's say that we've got some V that looks like this. I've imagined that I've kind of taken some lift of it, which is a Lagrangian submanifold, and now I want to ask, what kind of holomorphic disks can have boundary on this Lagrangian? And what do the projections look like underneath the map? So you can imagine like maybe, well, the disk of the boundary of a holomorphic disk is a circle. So I'm going to be looking at maps of circles to this tropical thing over here. So you can imagine maybe like one of them kind of goes like that, or maybe one of them goes like that. I actually don't know. I don't know how to parameterize any of these things. Or you can imagine, this type of behavior, or maybe a different type of behavior that you can imagine is a little more dramatic. You can imagine that when you have your holomorphic disk, the boundary of that holomorphic disk on the Lagrangian actually kind of goes around something. Okay, so kind of. When I look at the holomorphic disk, and I project it down to the SYZ base, I'll actually see the disk. And it turns out that these types of configurations are okay. There's no geometric principle that forbids them from happening. But these configurations are not okay. In fact, holomorphicity of the disk will prevent you from having this type of behavior. I can put that up in a precise lemma. There exists a family of almost complex structures, JA, such that for any beta, a class of a potential holomorphic disk, there exists B, such that for all A greater than or equal to B, the moduli space of beta holomorphic disks with respect to the complex structure JA is empty if the boundary class of beta is not zero. So if I look at this disk class and it happens to trace out some interesting homology in the base, then I can find some almost complex structure that will make that class disappear, make a holomorphic disk disappear.
Jeff, are you
Yes.
going to say a word about the proof of the lemma, or?
Yeah, of course.
Okay.
Yeah, so let me tell you what the complex. I mean, I'll sketch it out. I'm not going to do all the calculus because I'm very likely to make a mistake. But I'll sketch out the proof. So I guess I first have to tell you what this almost complex structure is. And the one that I'm going to take is the one which takes the fiber and makes it look very big. So the almost complex structure JA, when applied to directions in the base, will be A inverse times the corresponding direction in the fiber. And JA, when applied to directions in the fiber, will be minus A times the direction in the base. So the standard complex structure is when A is set to 1. And then as I increase A, I'm kind of skewing the complex structure so that the fiber directions seem to be very large compared to the base directions. Okay. And then with respect to this almost complex structure, you can do the following computation, which is that if you look at the symplectic area of beta, so this is equal to the integral over the disk of the pullback of omega. Okay, and then you expand out what the Cauchy-Riemann equation is for this, and you use this explicit substitution, and then I think you have to apply maybe AMGM inequality once or something. And then you get that this is greater than or equal to A times the area of the projection of U divided by the dimension of Q. Okay, so on the one hand, I have a constant quantity, right? Omega beta doesn't depend on A at all. On the other hand, I have a quantity where this area over here can be bounded away from 0 because I've said that my disk has some kind of non-trivial homology that is going around. So there's some kind of minimal area that this disk could have in the Q plane. So this is area as measured in Q. On the other hand, I'm taking that quantity, I'm multiplying it by A. Right, so eventually there's going to be A big enough that this inequality has to be violated. So once I choose A that large, then there are going to be no holomorphic disks living in that class. So I haven't seen this statement written up before, or this kind of tropicalization statement written up before, but I learned of it from Brett Parker originally. So this is the same kind of statement that says that if you look at tropical curves with boundary on a Lagrangian torus fiber, if you look at holomorphic disks with boundary on a Lagrangian torus fiber, that they tropicalize under a suitable choice of almost complex structure. Okay. Great, 10 minutes. So that brings us to the last part of the talk, which is superabundance. Or maybe non-superabundance. So again, the setup is that I'm going to have some tropical subvariety V inside of Q. Then there are the following maps of vector spaces. So if I sum over all the vertices of V, there's a map from let's see, let me write this out in kind of all the detail. So, So, let me describe what these vector spaces are. So at every vertex V, I have the set of integral tangent vectors of my manifold Q at V. And at over every edge E, I also have a set of integral tangent vectors, I guess integral tangent vector fields over the edge E. And there is a mapping from integral tangent vectors over any vertex, to integral tangent vector fields over any edge. Okay. And then, oh, I wish I had written this a little bit further. Let's map that to a vector space curly A. So I'll let curly A be the co-kernel of this map. So these are the set of all integral tangent vector fields which do not arise from taking integral vector fields of integral vectors at the vertices and pushing them forward. All right. There's another map over here. Which goes from the integral tangent vector 2E to the integral tangent vectors of Q over E. And we say that V is non-superabundant if this composition phi surjects. The version of non-superabundance that I'm using here is the one that is used by Chung, Fantini, Park, and Ulrich on their paper that shows that non-superabundance applies derealizability.
So is it easy to draw like an example in
Of something which is superabundant?
or both ideally?
So non-superabundant is easier to draw. Kind of the generic thing that you draw will be non-superabundant. Superabundant is harder to draw. The smallest example of that, I think the only examples you only start seeing them in dimension 3. I could try, but it would probably be more confusing to look at my picture than to look at the original source. So if you Google Michalkin superabundant elliptic, then it'll give you an example of cubic in a tropical cubic in P3, which is superabundant. And the picture is drawn with a computer, so you can actually
Okay.
see it. Sorry.
Thank you.
I don't understand this map from the vertices into the edges. Is it just, why is it not surjective?
Why is this map not surjective?
Yeah.
Because because if I take a vector here, it'll get mapped to this edge and to this edge.
Okay.
And you could imagine that there's some kind of
Cancellation going. I see. Okay.
cancellation that comes up when you have cycles. Yeah. So when the curve is genus 0, this thing is surjective, and then this target over here, A, disappears, and you're always non-superabundant. So yeah, so if you're genus 0, you're automatically a non-superabundant. So you can take this condition over here. Each one of these things can be used to describe a portion of the cohomology of a tropical Lagrangian. And by computing the cohomology of a tropical Lagrangian with respect to a covering, which is defined by small neighborhoods of the vertices and small neighborhoods of the edges, you get the following lemma. Is that if V is non-superabundant, and the following sequence is exact. Um, and intervention 3, if you massage this exact sequence by using a sequences of Poincare dualities and using something about the cohomology of the torus, you get the following corollary. Is let V be inside of Q. Dem V equals 1. Then Q equals 3. And trivializable. So that there's a map, an argument map from XA to P star Q mod N. Then, so H1LV includes into H1V plus H1 T star 0 Q mod N. Okay. Where on the first factor, the inclusion is by pi A, projection map. And on the second factor, it's by inclusion into X and then applying the argument. Okay. Great. So the last part is to put these three pieces together. So under the condition of the corollary, LV is unobstructed. Okay, so why is that? Okay, to show that it's unobstructed, I need to show that whenever the boundary of my disk is not zero, I have an empty moduli space. Okay, so suppose the boundary of beta is not equal to zero. In H1 of L, V, then by the lemma, oh, sorry, then by this lemma over here, let's call this lemma 1. By lemma 1, we have that, okay, well, this map is injective. So either I have a non-zero class in H1V, or I have a non-zero class in T star Q mod N. So either the projection to the base of this boundary class is not zero, or the argument of this boundary class is not zero. Okay, but this argument of the boundary class has to be zero. Because well, the boundary of the argument of beta is equal to the boundary of beta. Okay, so I'm in this case over here. So I have that pi boundary B is not equal to zero. So by lemma 2, and pick KA such that this moduli space is empty. By lemma 3. So I satisfy the conditions of lemma 3. That implies LV is unobstructed. Okay, so in summary, what's happening? When you have this unobstructedness condition, the tropical Lagrangian has first homology, which is basically determined by homology that lives in the base direction and homology that lives in the fiber direction of XA. If you were superabundant, then your tropical Lagrangian is glued together in some kind of clever way that you pick up extra interesting H1 classes. But in the non-superabundant case, the only homology that you can have is in the base or in the fiber. And then you ask, can I bound holomorphic disks in the fiber direction? And the answer is no, just simply topologically. The fiber is a torus, and you can't have a disk in a non-trivial homology class of the torus. And then you ask, can I bound disks in the base direction? And the answer there is also no. And the reason for that is that, well, we expect holomorphic disks in the base direction to tropicalize. And if I take a disk and I tropicalize it, it has no interesting homology. It fibers over a tree. There's no homology in the base direction, there's no homology in the fiber direction. And then FO cubed tells you if I have no homology in the base direction, no homology in the fiber direction, and I apply kind of a clever enough induction argument for building a bounding cochain, then my Lagrangian is unobstructed. Okay. And I think I am over time, so I will stop there. Thanks.
Thanks a lot. So I think we have applause and stuff. So questions?
I have a question about this last argument that you have a disk. You cannot have a disk bounding like circle in a fiber.
Yeah.
Suppose your base manifold has like singularity.
Yes.
So can you say anything about and like is anything true in that case?
No, nothing is true in that. This whole argument falls apart then. Yeah.
Because of this statement that you can have a disk which bounds like a non-trivial cycle in a fiber.
Yeah. So I mean, actually, it falls apart in a bunch of places. That's one component. Another component is when I described for you the almost complex structure over here, I took the fiber directions and I kind of blew them up to be very big. But I can't do that as soon as I have a singularity. Then I don't have the translation invariance on the fiber, or I don't have the multiplicative action that allows me to just scale the fibers that way. So you'll also this lemma over here will also not end up being true. So you can have disks that that trace out stuff in the base and continue to do so for a long time as well. Yeah. So an example which you might like is if I take something like P2, I take its moment polytope, I take its Lagrangian torus fibration that comes from the standard from the T2 action, and then I modify the almost toric diagram by adding in some singularities. Then you can create there's a Lagrangian submanifold that lives over this tropical curve. And it must bound a holomorphic disk, which sweeps out that cycle, no matter what complex structure you choose. So when you start adding singularities to the base, or when you start making the fibration non-trivial, so here I guess I've collapsed the fibers, then holomorphic disks with boundaries on tropical Lagrangians do not tropicalize. So there's some kind of probably much more complicated process going on in order to figure out exactly when you can remove the counts of these disks.
Okay, thank you.
But will that disk be Maslov 0?
That's a Maslov 2 disk in this case.
Okay, so they don't actually obstruct in that case, right? Just like weakly obstruct, but not.
Yeah, this one is weakly unobstructed. I mean, right? You can see that there has to be a disk here. I mean, just for some kind of topological reasons. So you know that it has to bound at least 3 different homology classes of disks. And then if I look at the torus and I pick any 3 homology classes, one of them winds non-trivially around the meridional direction. So that means that the boundary of one of these disks needs to wind around this direction of the torus. So there's nothing that you can do to get rid of that disk.
So maybe I'll ask a question now. So in the superabundant case, do you know they are obstructed, or you just don't know they are unobstructed?
Right. So, I mean, there are some superabundant curves which are realizable. I mean, kind of the expectation that you have is that in like the superabundant family, there's some subfamily of superabundant, but for magical reasons still being realizable. So you can't tell simply from non-superabundance. Sorry, you can't simply say that because you are superabundant, you're not realizable. What you can say is that if you are non-realizable on the B side, then you have to be obstructed on the A side. Because we have this implication that A realizability implies B realizability.
Okay, so you have concrete examples of obstructed Lagrangians.
Yeah, we have concrete examples of obstructed tropical Lagrangian submanifolds. And they
So
come
for
from
instance,
taking.
you're saying that this this elliptic curve in R3, so this is one of the examples which is obstructed Lagrangian.
Yes, that's an example of obstructed Lagrangian, yeah. So what you see in that case is the deformation space of a Lagrangian submanifold is just given by the size of its H1. And for tropical Lagrangian submanifolds, that dimension is exactly twice the dimension of the tropical deformation space. So there's no difficulty lifting tropical deformations to the Lagrangian deformations upstairs. And what happens, or what I believe happens, is when you get to the when you're in the superabundant family and you get to the one which is actually realizable, you compute the Floer cohomology of that tropical Lagrangian, and even though its homology has rank which is too high, its Floer cohomology will have smaller rank. So some of those holomorphic disks are going to start killing out what the superabundant directions were.
And sorry about the ignorance. So in this example you've been talking with Ilya. So what is exactly the Lagrangian? Is it a torus or?
Yeah, it's the topology of the Lagrangian. I have no idea. It is some 3 manifold. I can tell you that it's locally cat 0. But I think we don't have, I don't know, some concrete description of the topology of it, which is any more concrete than here's the tropical curve and here's a recipe for building a manifold out of it. I can attempt to draw this thing if you would like.
Or Lina, I can draw it for you. I can come to your
maybe you probably have people who are better experts at drawing tropical curves than me. So yeah, I'm just gonna impress myself. I'll stop.
Okay. So other questions? No? Okay, so I think that's it for today. Thanks a lot, Jeff.
Thank you very much.